Good morning. So in this lecture we will further try to understand the NMR spectroscopy more deeply. NMR spectroscopy, as we studied in the previous lecture, is not a combination of these three things. We use a radio wave light radiation, electromagnetic radiation, and a fixed wavelength. Then we studied the nuclear spin, what is there in matter, in compounds or molecule, what are there in compound or molecule, ultimately atom, what is there in atom, that is related to NMR, that is nucleus, nucleon, and further in nucleon we have protons and neutrons, and protons are a charged particle having its own magnetic field. Third thing we involved is a magnetic field which we applied externally. So this interaction of these, we use radio wave radiations, and then we studied nuclear spin. How the nucleus means nucleons, they spin and generate its own magnetic field, and then we studied how that magnetic field interact with the external magnetic field. So in this lecture we will further clarify more things related to this magnetic field. So now this is a nucleus, this is your proton, a charged particle. So if we say that if I is the net nuclear spin, then nucleus can have 2I plus 1 spin states. So I agar half hai, it's half, then spin states become 2. Why, when we apply this, these are the you can say magnetic moment, tiny bar magnets in the absence of external magnetic field, and when we apply magnetic field, why they align them into only 2 ways, not in 3 ways or 4 ways? Why in 2 ways? An alpha and a beta, I explained in the last lecture. Alpha has lower energy, plus isme spin is plus half, and beta spin is minus half. So why these randomly distributed magnetic moments or these tiny bar magnets, they arrange themselves into only 2 arrangements, 2 alignments? The reason is that we calculate the spin state by using this 2I plus 1. So I is your spin state. If it is half, you can put the value, you will get 2 spin states. So when there is 2 spin state, that is either is aligned along the direction of the external magnetic field. If the external magnetic field direction is like this, so this is your external magnetic field. So alpha is in the same alignment as with the external magnetic field, and beta is opposite. Beta you can say, you can write here like this. Beta is an opposite direction to that of the external magnetic field. Only 2 spin states. When we get somewhere when we get a triplet means when we apply a magnetic field, 3 alignments are possible. So what will be those 3 alignments? One is with the magnetic field, other is against the magnetic field, third is neutral, like this, perpendicular to the magnetic field. That is called triplet state. Okay, so when any proton it spins, it generates 2 types of magnetic moment. You can say angular momentum. It generates 2 types of angular momentum. So this is a nucleus, and electron is revolve around the nucleus in this direction, and this electron also spin. I am explaining in terms of electron only. Okay. So for electron there are 2 types of angular momentum. One is the orbital angular momentum. Orbital angular momentum means when this electron revolve around the nucleus. Just like Earth revolve around the Sun, it also revolve around its own axis. This electron has the same nature. It revolve around the nucleus. When it revolve around the nucleus, it generate orbital angular momentum. But when it spin along its axis, either plus half or minus half, it generates nuclear spin angular momentum. So there are 2 types of angular momentum, orbital and spin. Orbital angular momentum for electron, not for proton. For proton we will discuss only the spin angular momentum, because spin only. For electron I am explaining that there are two types of angular momentum. One is orbital, when the electron revolves around the nucleus it generates some that momentum, that is called angular momentum, orbital angular momentum. You know what is the difference between momentum and angular momentum? Momentum is in straight line, angular momentum is in circular motion. Only this is the difference. So for electron we have a two type of angular momentum. Orbital angular momentum, due to its movement in the orbital around the nucleus, when it revolves around the nucleus it generates its orbital angular momentum. Second is, when it revolves around the nucleus it also spins. So because of that spin it generates its spin angular momentum. So the total angular momentum for electron is sum of the orbital angular momentum and spin angular momentum. That's also known as nuclear spin angular momentum. But for this proton we have only nuclear spin angular momentum. Okay. So here is the formula. You can see mu equal to gamma I. What is mu? Mu is your magnetic dipole moment. From where it comes? Due to its charge and spin of the proton. If you look at the nucleus, what is magnetic dipole moment? That's magnetic dipole. What is magnetic dipole? That is because of its charge and spin is called magnetic dipole moment. It is represented by mu. And it is equal to gamma into I. This gamma is a parameter, is a constant for a particular type of nucleus, is called Gyromagnetic Ratio. Gamma is a constant value, is constant for particular type of nucleus, and it is known as Gyromagnetic Ratio. What is I here? I is nuclear spin angular momentum. So mu, this mu is the vector quantity. Vector quantity means it has direction. Similarly, I is also a vector quantity. So we can write mu like this, because when we apply a magnetic, suppose here is the nucleus which contains proton and neutron, and when we apply an external magnetic field, so we can apply it along one direction, either along x-axis or along y-axis or along z-axis, because it is a vector quantity. Magnetic dipole moment is a vector quantity, it depends upon direction, so it may have three directions as per the coordinates x, y, z. So mu x, mu y, mu z, these are the three magnetic dipole moment along the three axes. Similarly, you can split I, that is your nuclear spin angular momentum, along Ix, Iy and Iz. Okay. So when we apply a magnetic field, this magnetic dipole interact with the external magnetic field. External magnetic field is taken as say external magnetic field H naught. So when we apply a magnetic field, this magnetic dipole interact with the external magnetic field, and energy of interaction is given by the formula. What will be the energy of this interaction? Because the nucleus which is present at the center of the atom, that has a proton, and proton has its own magnetic moment. That magnetic moment interact with the external magnetic field. When we apply external magnetic field either from x-axis or y-axis or z-axis coordinates, it interact with that magnetic field, then the energy of interaction E, that is written as minus mu H naught. Mu dot H naught. This is a dot product. So we can write it like along the various axes, we can write it like U is equal to X, HX plus Y, HY plus Z, HZ. Dot product means we can write like it like this. Okay. So here we have a H naught, that is an external magnetic field. That also split into three components, that is Hx, Hy, Hz. Now from which direction we are applying? Suppose we are applying the external magnetic field in the Z direction, then what happened to X and Y component? They become zero, they do not exist. And only this component exists, mu z, x z. Okay, so energy equal to this energy equal to minus mu dot h naught. Both are vector quantity. We may replace this mu by this because mu is equal to gamma I. So you can write it here minus gamma Iz, and now we can write here Hz. When we apply the external magnetic field along the z axis. Okay, so if your I now we can understand from this that if your I is negative, or you can say plus half, that is for alpha, then the energy will be negative. When you put here plus half, then energy will be negative. Negative means energy will be less, as we can see here. So alpha state has lower energy. When we put I is a minus half, that we designate as beta, then the energy become more, it become positive. When you put it here, minus half, minus become plus is plus. So that's why the energy of beta is more than alpha. So this is the main point in terms of the three-dimensional from where the external magnetic field comes. Okay, so we have a nucleus, again I am repeating this, and we are applying H naught from any direction, from x-axis, from y-axis, from z-axis. Suppose we apply the external magnetic field along x-axis, or sorry, z-axis. What happened to these two? They do not exist. So that's why your energy become equal to mu. You can write here gamma Iz Hz. H is your external magnetic field. So from here we can draw this structure like alpha state has lower energy and beta state has higher energy. Okay, so this is the overall idea of NMR that we studied. First is the take sample which contain molecules in which the atoms have non-zero nuclear spin. Non-zero nuclear spin means NMR active nuclei in which the value of I is more than 0. Second is put the sample in magnetic field that we applied externally. Let's say it's applied along the z-axis. Third is when you apply the magnetic field to a sample or to a molecule, the molecules get distributed into two populations, two groups, alpha and beta. One set of nuclei in the alpha state, other set in the beta state because of the interaction with the magnetic field. Because every molecule which is present in a sample that has a number of protons, and every proton has its own magnetic field because of its charge. So that magnetic field of the protons that interact with the external magnetic field, when it interacts with the external magnetic field, as we have studied that there are two possible states, spin states, that is alpha and beta. And we also calculated the energy of these two alpha states, like alpha state has a negative energy, lower energy, then a beta state has a positive energy. So molecule get distributed into two groups or two populations with one set of nuclei in alpha and other in the beta because of interaction. And the last is, now next thing is to take the molecule from the ground state to excited state. This is called flipping of spin. We have to take the molecule from the ground state to excited state by applying energy we are using the radio waves. So when this transition takes place, when the molecules go from alpha to beta state, energy is absorbed. More the amount of energy observed, more is the sensitivity, we can say, of the NMR spectroscopy. So now in the next topic we will discuss how the sensitivity be increased. Like this amount of energy absorbed, that is delta E, that is equal to the population difference between the alpha and beta state. If the number of molecules in alpha and beta state are equal, there will be no absorption of energy. Less absorption of energy means weak signal, weak peaks. More absorption of energy means strong, clear signal. So means our target is to generate the population difference between alpha and beta. There must be some difference between alpha, like 10 molecules are in alpha and 9 molecules are in beta. No, there is not too much difference. Then the sensitivity become less. So main target is we have to increase the population difference between the alpha state and beta state so that sufficient large amount of energy is absorbed and a clear and you can say high intensity peaks that is formed in the appeared in the spectrum. So next we will try to understand this concept that how to increase the population difference between alpha and beta. Suppose at alpha state there are 5 molecules, beta state there are 5 molecules, then there will be very limited chances that a molecule go from alpha to beta. In general, according to Boltzmann distribution law, in general, alpha state has more number of molecules as compared to beta because alpha is more stable than beta. Even then, there must be a sufficient population difference between the alpha and beta so that a sufficient large amount of energy is absorbed and clear signal appeared in the spectrum. Next is sensitivity of NMR. Sensitivity means how the molecule they respond towards NMR spectroscopy. That we can judge from the intensity of peaks, clarity of peaks. So basically sensitivity of NMR is less than as compared to ultraviolet and IR spectroscopy. So this depends upon the population difference between alpha and beta spin state. So as we have already discussed that when we apply a magnetic field to a molecule, there is a distribution of spin states. Some molecules having a spin of plus half, some have minus half. So plus half they go to alpha and minus half go to beta against the external magnetic field or with same alignment with the external magnetic field. So the difference is delta E. Here you can see in the formula delta E, that is the difference between the energy state. Okay. So according to Boltzmann distribution or Boltzmann distribution law, at equilibrium conditions, there is always more population in the ground state compared to excited state. These are under standard conditions. We will always have more nucleus sitting in the ground state than in the excited state. But this ratio, we must increase this ratio, like population difference, that must be increased, because more the population difference between the alpha state and beta state, more energy is observed. That we are using a radio wave, more energy is observed, and more energy is observed means that become more sensitive and more intense peak will appear in the spectrum. So to increase the population difference, we must increase the energy gap. First, here from this formula we can analyze and we can find out the factor which affect this. Like here you can see in this formula, this is Boltzmann distribution, n half plus half n minus half alpha beta by alpha E equal to delta E by k. K is your Boltzmann constant. Boltzmann constant. P is your temperature on Kelvin scale. Delta E is the energy difference between these two spin states. So this can be written like this. So we have gamma H, this H naught external magnetic field, P temperature. From here you can see that there are many factors which affect this. Okay, that factor is, if we want to increase the ratio n beta by n alpha, so we have three factors. First is that suppose these are the two levels, energy levels, and here we have alpha and here we have say beta. Population difference is less. First thing is what to do is to increase the energy difference. When you increase the energy difference, more molecule will stay in the ground state, less molecule go into the excited state, so their population difference will automatically increase. When the population difference increase, it's easy to take the molecule from the ground state to the excited state. Or it's very easy because their population is very less. Because in NMR spectroscopy, when we apply energy, there is a both process like simultaneous excitation and simultaneous emission that take place. Means some molecules, they go from alpha to beta state. When they go from alpha to beta state, they absorb energy. This is called absorption. But some molecule, because at beta state energy is more, they come back to alpha state. Simultaneously they come back to alpha state. And when they come back from beta to alpha state, they emit energy. That is called emission. So simultaneously emission and excitation, absorption and emission take place. So total net energy observed will depend upon the difference in population, like how many nuclei are in the ground state minus the nuclei in the excited state. If they are equal, then there is no net excitation and signal will be zero. If the population is equal, there will be no net energy change, net energy observed, there is no net excitation, then there will be no signal. That means no energy will be observed. If no signal means no energy, because signal will appear only when there is a flipping take place. When the electron that go from alpha to beta state, then only the signal will appear in the NMR spectrum. If there is no signal, it means there is no energy absorbed, and this flipping take place by the absorption of energy, that is a radio wave. Okay. But if the difference in the population between ground state and excited state is not zero, means if ground state is more populated than excited state, then there will be more number of nuclei absorbing than the nuclei coming down. So more number of molecules they are going up than the molecule going down. It means there is net absorption of energy. When there is a net absorption of energy, signal will only appear then in the spectrum. Otherwise, there will be no signal. So our target is that is in other word, that is called the sensitivity. Okay. So we have to increase the absorption of energy. That can be done by increasing the population difference. And one way to increase the population difference is that we have to increase population difference means we have to increase alpha state and decrease beta state. Population difference that will create. Okay. So by increasing the energy gap between two, alpha and beta, we can increase the population difference. Then obviously when there is more energy gap, more energy will absorb, and then more energy will absorb means more clear signal will appear in the NMR spectrum. So what we can do, other things to increase the population difference, that is first is going toward higher wavelength. Going towards higher wavelength. Second is increasing the external magnetic field. What will happen when we increase the external magnetic field? The gap between the two energy level that increases. Okay. Third is by decreasing the temperature. Decreasing the temperature. This term decrease, then overall the term will increase. Increase means beta will be less than gamma. This increase, overall decrease, negative sign increase. So this will increase. Okay. Similarly, delta E, when we increase the external magnetic field, this thing will happen that the difference between alpha and beta state that will increase. Going towards longer wavelength or higher wavelength, that may also increase the population difference between the two spin states. So these are some factors which may increase the population or sensitivity of NMR, because sensitivity is nothing but is depend upon the population difference between the alpha and beta. More the population difference between alpha and beta, more energy is observed, and when more energy is observed, it means clear signal will appear. If there is no difference between the alpha and beta state, equal number of molecules existing in alpha and beta, there will be no net energy absorption take place and signal will be zero. Okay, so this is about the sensitivity of NMR spectroscopy.